Right now, over 1 million people are suspended in the sky, trusting their lives to a machine they barely understand. Underneath their wings hangs a piece of engineering so massive, it is wider than the entire fuselage of a Boeing 737. In a single second, this mechanical beast swallows over a ton of air. Deep inside its core, jet fuel burns at 600 degrees Fahrenheit. It is a temperature perfectly capable of melting the very metal the engine is built from. By the strict laws of physics, this colossal structure should turn into liquid and violently tear itself apart in midair, raining molten steel down to the earth. Yet, it operates flawlessly for tens of thousands of hours, crossing oceans and continents without a single stutter. How exactly do human engineers forge a 100,000 horsepower beast that survives inside its own inferno? The modern aerospace factory does not look like a traditional manufacturing plant. There is no soot, no uncontrolled sparks, and no grease on the floor. It is a sterile, climate-controlled environment that closely resembles a giant surgical laboratory. Here, inside massive clean rooms, engineers are assembling the most powerful, complex, and dangerous internal combustion machines ever created by human hands. To truly understand the paradox of the modern jet engine, you must first comprehend its sheer, terrifying scale. Take the GE9X, the power plant designed for the Boeing 777X. The front fan alone spans over 11 feet, or 3.4 meters, across. If you were to walk into the intake of this engine while it was turned off, you could stand up entirely straight with room to spare. The engine is so large and generates so much thrust that Boeing had to design folding wingtips for the aircraft just so it could fit into standard airport gates. This single engine generates over 100,000 pounds of thrust. That is enough raw kinetic energy to keep a fully loaded aircraft. Weighing nearly 800,000 pounds, suspended in the incredibly thin air of the upper atmosphere. When operating at maximum takeoff power, this mechanical leviathan breathes in roughly 1.2 tons of air every single second. To put that staggering number into perspective, it would vacuum all the breathable oxygen out of a massive sports stadium in less than a minute. But swallowing the air is only the first step. What happens next is where the laws of nature are manipulated, constrained, and pushed to their absolute breaking points. When you look at the massive fan spinning at the front of a passenger jet, you might assume all that air is going straight into the fire. In reality, modern engines rely on a brilliant physical workaround known as the bypass ratio. In an engine like the GE9X, roughly 90% of the air sucked in by that giant front fan never actually enters the fiery core. Instead, it bypasses the core entirely, flowing around the outside to produce the vast majority of the engine's silent, efficient thrust. But it is the remaining 10% of the air that is forced into the engine's dark, tightly packed core, that creates the ultimate engineering nightmare. This small percentage of air is violently forced through a labyrinth of increasingly smaller compressor blades. These blades spin at phenomenal speeds, slicing and violently squeezing the air into a space completely unnatural to its normal state. As the pressure drastically rises, so does the kinetic energy of the air molecules. The friction is so intense that even before a single drop of fuel is introduced, the highly compressed air reaches temperatures exceeding 100 degrees Fahrenheit. The metal compressing it is glowing red hot simply from the sheer physical force of the air itself. Then, this superheated, highly volatile air reaches the combustion chamber. Here, jet fuel is continuously sprayed into the pressurized hurricane and ignited. It is not a series of controlled, rhythmic explosions like you would find in the engine of a sports car. It is one continuous, raging, unstoppable firestorm. The temperature inside this chamber skyrockets to approximately 600 degrees Fahrenheit, or 2000 degrees Celsius. Immediately behind this roaring inferno sit the high-pressure turbine blades. Their job is to extract energy from the blast, keeping the compressor spinning and the engine alive. They are forged from state-of-the-art superalloys, primarily based on nickel, representing the absolute pinnacle of human metallurgy. But here is where we hit a glaring, terrifying mathematical wall. The absolute maximum melting point of these advanced nickel alloys is roughly 400 degrees Fahrenheit. The artificial firestorm blasting against them is over 200 degrees hotter than the point at which the metal turns to liquid. If you put these blades inside this engine under normal physical rules, they should not just fail, they should turn into a shower of liquid shrapnel within a fraction of a second, destroying the aircraft instantly. Furthermore, engineers actually want the engine to run this hot. According to the laws of thermodynamics, specifically the Carnot cycle, the hotter the combustion, the more fuel efficient the engine becomes. The entire aviation industry is constantly trying to push the temperature higher, deliberately pushing the metal closer to its own destruction. Yet, the blades survive. They spin thousands of times per minute, enduring this impossible heat for years of active service. To understand how a machine can survive a fire that should mathematically destroy it, we have to look away from the massive factory floor. We have to zoom in much closer, down past the mechanics, past the chemistry, straight into the invisible, atomic structure of the metal itself. If you were to take a standard piece of aerospace-grade titanium or steel and look at it through an electron microscope, you would not see a smooth, uniform surface. You would see millions of microscopic crystals pressed together in a chaotic, interlocking mosaic. The microscopic borders where these crystals meet are known in metallurgy as grain boundaries. At room temperature, these boundaries are completely harmless. But inside the high-pressure turbine of a jet engine, the environment is fundamentally hostile to the existence of solid matter. Each individual turbine blade is relatively small, roughly the size of your hand, and weighs just a few pounds. However, when the engine is operating at full takeoff power, this central core is spinning at well over 10,000 revolutions per minute. At this terrifying speed, the centrifugal force acting on a single blade is equivalent to hanging a fully loaded London double-decker bus from its tip. Now, imagine subjecting that blade to the weight of a bus, while simultaneously blasting it with an artificial hurricane that is 200 degrees hotter than the metal's natural melting point. Under this combination of extreme mechanical stress and thermal agony, the grain boundaries become fatal microscopic flaws. The heat weakens the borders, and the centrifugal force physically stretches the metal apart. Engineers call this terrifying phenomenon creep. Within minutes, the blade would deform, strike the outer casing at supersonic speed, and violently shatter. Standard metal simply cannot exist here. To solve this paradox, aviation engineers had to alter the fundamental laws of metallurgy. They had to completely eliminate the borders. First, they engineered a new class of materials known as superalloys. They started with a base of nickel and began alloying it with some of the rarest and most expensive elements on Earth, most notably rhenium. Rhenium has one of the highest melting points of any element and acts as a microscopic glue, binding the atomic structure of the nickel together even when the heat demands that it turn to liquid. But the chemical recipe was only the beginning. The true miracle lies in how these blades are manufactured. Deep inside high-security foundries, modern turbine blades are not stamped, forged, or carved. They are grown. Using a highly classified version of the ancient lost wax casting method. A precise ceramic mold of the blade is created and placed inside a highly pressurized vacuum chamber. Molten superalloy is then poured into the top. But at the very base of this ceramic mold is a tiny, meticulously engineered channel shaped like a pigtail spiral. As the molten metal slowly cools from the bottom up, multiple crystals begin to form and race upward through the channel. But the spiral acts as a microscopic, physical filter. As the growing crystals navigate the tight, twisting turns, they block each other out. Ultimately, only one single, unbroken crystal manages to navigate the entire spiral and emerge into the main body of the mold. As it cools, it forms the entire blade. Because the entire structure is literally one single crystal, there are absolutely no grain boundaries. There is no microscopic weak point for the heat and stress to exploit. But even a single, rhenium-infused supercrystal is still a metal. And the combustion air is still mathematically hotter than its physical melting point. So, engineers deploy one final, brilliant illusion. Using highly advanced electrical discharge machining, a process that uses electrical sparks to precisely erode metal, hundreds of microscopic holes are drilled into the surface of the blade. The blade itself is actually hollow. During flight, relatively cool air is bled from the front compressor, channeled through the hollow core of the spinning turbine blade, and forced out through these tiny pores. This creates a phenomenon known as film cooling. It generates an invisible, microscopic force field, a thin film of cold air that completely wraps around the metal. The blazing free, 600-degree Inferno never actually touches the blade itself. It is a masterpiece of thermal deception, and it is the only thing standing between a safe journey and a catastrophic mid-air explosion. Yet, surviving the Inferno is only half the battle. At the very front of the engine, the massive fan blades that pull the air in face a completely different physical limit, weight and gravity. To generate enough thrust to lift a Boeing 777X, the front fan must be massive. But if those 11-foot blades were forged from solid titanium, the engine would be far too heavy to fly efficiently, and the centrifugal force would rip the central hub apart. The solution was a radical shift away from metal entirely. Today, these massive front fans are built from advanced carbon fiber composites. Inside highly restricted facilities, robotic arms precisely stack thousands of ultra-thin layers of carbon tape. The arrangement is then injected with a high-tech epoxy resin and baked inside a massive industrial autoclave under immense pressure. The resulting fan blade is lighter than aluminum, yet vastly stronger than structural steel. However, carbon fiber is brittle against sharp impacts. And at takeoff power, the outer tips of these massive blades spin so fast they actually break the speed of sound. Hitting a raindrop, a hailstone, or a bird at supersonic speeds would shred the composite material. To prevent this, the very front edge of the blade is wrapped in a razor-thin layer of space-grade titanium, a metallic sword edge designed to instantly slice through any debris before it can damage the carbon weave. We have now forged components that ignore heat and defy gravity. We have manipulated metal at the atomic level. But possessing perfect individual pieces is not enough. You must now combine tens of thousands of them into a single, breathing machine. And as we step onto the final assembly floor, the margin for error shrinks to a scale completely invisible to the human eye. How exactly do human hands assemble a multi-ton rotating machine? Knowing that a misalignment the width of a human hair could cause it to tear itself apart at 35,000 feet? To truly appreciate the violence hidden inside a modern jet engine, you must understand what happens to the air the moment it slips past the giant front fan and enters the dark, heavily armored core. It does not simply flow backward. It is violently tracked, sliced, and mathematically crushed until it transforms from a life-giving gas into a highly volatile, weaponized force. This transformation takes place inside the compressor. The compressor is not a single spinning wheel. It is a dense, intricate labyrinth of metal, consisting of alternating rows of spinning rotor blades and stationary stator vanes. In a large commercial engine, there can be up to 14 sequential stages of this. With each row the air passes through, the physical space it occupies becomes tighter, and the blades become progressively smaller. In a modern engineering marvel like the GE9X, the overall pressure ratio reaches a staggering 60:1. Imagine taking the entire volume of air inside a large living room and violently crushing it down to the size of a standard carry-on suitcase, all within a fraction of a second. As the air is squeezed to this extreme density, its physical properties fundamentally change. It begins to behave less like a gas and more like a fluid. The immense friction and the rapid compression cause the temperature to spike dramatically. Even before a single drop of aviation fuel is introduced, the violently compressed air blasting through the final stages of the compressor reaches temperatures exceeding 100 degrees Fahrenheit. The metal walls containing this air are glowing cherry red simply from the sheer, brute force kinetic energy of the compression itself. But squeezing air this aggressively creates a terrifying aerodynamic problem. Nature hates high pressure. Air naturally wants to move from an area of high pressure to an area of low pressure. In a jet engine, the highest pressure is at the back of the compressor, and the lowest pressure is at the front intake. The air literally wants to violently reverse direction and blow straight out the front. If the pressure builds up incorrectly, or if the airflow is suddenly disrupted by a turbulent gust of wind outside the aircraft, this aerodynamic mutiny actually happens. This phenomenon is known in aviation as a compressor stall. When a stall occurs, the high-pressure air violently surges forward. The engine effectively chokes on itself. The result is a deafening explosion, accompanied by violent shock waves and massive flames shooting out of the front intake of the engine. In early jet engines of the 1950s and 60s, this happened constantly, often snapping blades and destroying the machine mid-flight. To prevent this catastrophic failure, modern engineers design a mechanical brain into the compressor casing, variable stator vanes. These are stationary rows of blades that physically pivot and rotate their angle in real time. Controlled by a complex digital computer, they constantly adjust the airflow like automated Venetian blinds adapting to a shifting hurricane, ensuring the air is always guided smoothly backward, no matter how much it wants to rebel. Once the air is successfully crushed to its absolute maximum density, it leaves the compressor and enters the absolute heart of the beast, the combustion chamber. Here, we encounter another impossible physical challenge: the superheated. Compressed air entering the combustor is moving at hundreds of miles per hour. Igniting jet fuel in this environment is the exact physical equivalent of trying to light a single match in the middle of a Category 5 hurricane and expecting it to stay perfectly lit. By all logic, the rushing air should blow the flame out instantly. To solve this, engineers do not just spray fuel, they atomize it. Highly specialized fuel nozzles inject the liquid aviation-grade kerosene as a fine mist of microscopic droplets. Simultaneously, mechanical structures called swirlers force the hurricane-force winds to curl back on themselves. They create a localized, perfectly controlled tornado inside the chamber. In the relatively calm eye of this artificial storm, the atomized fuel is ignited. Because of the swirling vortex, the flame remains completely stable. It is anchored in place despite the chaotic gales surrounding it, burning continuously and perfectly to extract every last ounce of chemical energy. However, designing these microscopic aerodynamic vortexes on a computer simulation is one thing. Manufacturing them in the real world is an entirely different nightmare. How do human hands and machines actually assemble a fuel nozzle so complex that a microscopic error in its geometry could cause the entire engine to tear itself apart at cruising altitude? For decades, the intricate fuel nozzles required to create that perfect, localized tornado inside the combustion chamber were an engineer's nightmare. Creating complex aerodynamic geometries out of solid metal is incredibly difficult. Historically, a single fuel nozzle was made by painstakingly casting and welding together over 20 separate, microscopic metal components. But inside an environment that resembles the surface of a star, every single microscopic weld is a potential point of catastrophic failure. The extreme thermal cycling, heating up to 600 degrees and cooling back down to sub-zero temperatures at cruising altitude, causes metal to expand and contract. Over time, a microscopic crack could form in one of those welds. If that happened, the fuel spray would become uncalibrated, the flame would destabilize, and the engine could literally melt itself from the inside out. To solve this, modern aerospace manufacturers had to abandon traditional machining entirely. Instead, they turned to a technology that sounds like science fiction: additive manufacturing, commonly known as industrial 3D printing. Inside sealed, argon-filled chambers, a mechanical arm spreads a layer of cobalt chrome metal powder, perfectly flat and completely uniform. This layer is thinner than a single human hair. Above it, an invisible, high-powered laser traces a highly complex mathematical pattern, instantly melting the powder into solid metal. Layer by microscopic layer, the fuel nozzle physically grows from the bottom up. The result is a single, continuous piece of metal containing incredibly complex internal cooling channels that would be physically impossible to carve, drill, or cast using traditional methods. It is 25% lighter, 5 times stronger, and possesses exactly 0 welds. With the components perfected, the final assembly begins. But this is not a traditional factory floor with flying sparks, heavy hammers, and oil on the ground. It is a climate-controlled clean room that resembles a sterile surgical theater. Here, the margin for error shrinks to a scale completely invisible to the human eye. Thousands of individual blades must be slotted into massive rotating discs by hand. The mechanical precision required here is terrifying. Consider the clearance between the tips of the spinning turbine blades and the static outer casing of the engine. To maximize thermodynamic efficiency, all the violently pressurized air must be forced to flow through the blades, pushing them forward. It cannot be allowed to leak around the edges. Therefore, the gap between the blazing hot, spinning metal and the static engine wall is incredibly tight, often less than a millimeter, roughly the thickness of a few sheets of paper. But a jet engine is not a static object. When the engine fires up and reaches maximum temperature, the metal blades physically expand due to the heat. Simultaneously, the immense centrifugal force stretches the blades outward. if the engineers miscalculate the gap by even a fraction of a millimeter. The expanding blades will aggressively scrape against the engine casing at supersonic speeds. The friction would cause them to instantly shatter, triggering a catastrophic internal explosion. It is a terrifying balancing act of thermodynamics and mechanical tolerances. Furthermore, this entire multi-ton rotating assembly must be perfectly balanced. Think about a standard household ceiling fan. If one blade is even slightly heavier than the others, the whole fan wobbles. Now, imagine a central core composed of thousands of dense metal parts, weighing thousands of pounds, spinning at over 10,000 revolutions per minute. If the weight distribution is off by even a fraction of an ounce, the resulting vibration will not just shake the aircraft, the kinetic energy will literally tear the engine off the wing in midair. To prevent this, the fully assembled core is placed into a massive dynamic balancing machine inside a reinforced concrete bunker. The core is spun up to operating speeds while lasers and highly sensitive acoustic sensors measure its rotation down to the micron. Technicians carefully add microscopic weights, or sometimes shave off tiny, dust-like slivers of metal, until the entire multi-ton assembly spins with absolute, perfect stillness. On the factory floor, the finished engine is an undisputed masterpiece of human engineering. It is mathematically precise, impeccably clean, and theoretically perfect. But theoretical perfection means absolutely nothing in the brutal, unpredictable reality of the open sky. Before this multi-million-dollar machine is ever legally allowed to carry a single human passenger, it must be dragged out of the sterile laboratory. It must be subjected to the most violent, destructive physical abuse imaginable. It is time to enter the torture chamber. The factory floor is a place of mathematical perfection. But theoretical perfection means absolutely nothing in the brutal, unpredictable reality of the open sky. Before any aerospace manufacturer is legally allowed to attach their machine to a commercial airliner, the engine must leave the sterile cleanroom. It is transported to a heavily armored, highly instrumented concrete bunker. Here, it will be subjected to a relentless, multi-million-dollar campaign of deliberate destruction. A jet engine cannot just operate perfectly in clear blue skies. It must survive the most violent forces of nature, and it must do so while keeping 400 people suspended miles above the earth. The first phase of the torture test is a simulation of extreme weather. An aircraft flying through a severe, high-altitude thunderstorm acts like a giant vacuum cleaner. To simulate this, engineers place the engine behind a massive grid of pipes and nozzles. While the engine runs at full takeoff power, they blast it with thousands of gallons of water every single minute. The volume is equivalent to a torrential, apocalyptic monsoon. Immediately after the water flood, they unleash a bombardment of solid, frozen ice balls directly into the intake. Inside the core, the compressor is instantly tasked with acting like an industrial ice crusher. While the combustion chamber must maintain its 600-degree firestorm while swallowing a literal river. Despite the onslaught, the engine barely stutters. The roaring flame refuses to drown. But water and ice are expected. Nature holds much darker surprises. In 1982, British Airways Flight 9 lost all 4 of its engines simultaneously while flying over Indonesia. The culprit was not a mechanical failure, but a volcanic eruption. The aircraft had flown into a high-altitude ash cloud. Volcanic ash is not like wood smoke, it is essentially microscopic, pulverized rock and silica glass. When millions of these microscopic glass particles get sucked into an engine, they hit the 600-degree combustion chamber. The glass instantly melts. This molten liquid rock flows backward and coats the high-pressure turbine blades. Within seconds, it solidifies, completely plugging those microscopic cooling holes we discussed earlier. The invisible force field of cold air fails. The engine suffocates and shuts down. To ensure modern engines can survive this nightmare, they are deliberately fed massive amounts of simulated volcanic ash and desert sand. Engineers have developed advanced ceramic matrix composite coatings, a microscopic layer of heat-resistant armor, to prevent the molten glass from sticking to the metal, allowing the engine to clear its throat and keep burning. But weather and geology are only part of the threat. Wildlife introduces an entirely different, highly unpredictable kinetic danger. One of the most dangerous threats during a high-speed takeoff is a bird strike. If a flock of large birds is sucked into the engine at 200 miles per hour, the impact energy is devastating. To prove the massive carbon fiber and titanium fan blades will not shatter under the impact, engineers employ a pneumatic cannon, famously known in the aviation industry as the chicken gun. They fire simulated, freshly thawed bird carcasses directly into the spinning blades while the engine is at maximum throttle. The sound of the impact is violently loud, but the razor-thin titanium leading edges act like massive supersonic swords, instantly slicing through the mass, while the carbon composite fibers flex to absorb the massive kinetic shock without fracturing. The engine might suffer internal damage, and the smell is notoriously horrific, but it continues to produce thrust. However, aviation regulators like the FAA and EASA demand an answer to a much darker, much more terrifying question. What happens if the absolute worst-case scenario occurs? What happens if a massive front fan blade actually snaps off while spinning at its maximum speed? This is known as the fan blade out test. It is the most violent, explosive, and expensive physical test in all of modern engineering. A single front fan blade of a GE9X or a Trent XWB is huge and incredibly heavy. If it breaks loose while spinning near the speed of sound, it immediately becomes a high-velocity, multi-ton missile. If this rogue blade breaches the engine's outer casing, it will slice straight through the aluminum fuselage of the passenger cabin, or tear directly into the wing's highly combustible fuel tanks, causing a catastrophic mid-air explosion. To prevent this nightmare, the outer casing of the front fan is wrapped in thick, incredibly dense layers of ballistic Kevlar, the exact same material used in military bulletproof vests, but woven on an industrial scale. Inside the concrete test cell, the engine is pushed to its absolute maximum limit. It is roaring, vibrating, generating over 100,000 pounds of thrust. The noise is lethal, deep at the root of one specific fan blade. Engineers have secretly planted a small, precisely shaped explosive charge. Without warning, they detonate the explosive. The titanium and carbon fiber blade violently snaps at the root. In a fraction of a millisecond, the massive piece of material slams into the outer casing with the kinetic energy of a runaway freight train. The impact is apocalyptic. The entire multi-ton engine violently shudders, twisting heavily on its massive steel mounting pylons. Sparks rain down as the unbalanced core instantly shreds its own internals. The noise is deafening, followed by a sudden, heavy silence. The engine instantly destroys itself. But as the smoke clears, the true victory of human engineering is revealed. The Kevlar containment ring held. The rogue blade was violently trapped inside the housing. Not a single piece of shrapnel escaped the engine pod. The engine died a brutal, sudden death, but it died completely safely. The aircraft, and everyone on board, would survive. Having survived the ultimate physical torture. This masterpiece of engineering is finally certified to carry human lives. It will spend the next 2 decades conquering the skies, crossing oceans daily without a second thought from the passengers sitting just feet away. But the story of human ambition does not stop here. As we look toward the horizon, the aviation industry is approaching a new, seemingly insurmountable physical wall. Today, engines like the GE9X and the Rolls-Royce Trent XWB stand as undisputed triumphs of modern engineering. They have pushed the absolute boundaries of what nickel, titanium, and carbon can physically endure. They operate with such profound reliability that we have entirely forgotten how inherently dangerous their internal environment truly is. But as we look toward the horizon of the 21st century, the aviation industry is quietly approaching a massive, seemingly impenetrable physical wall. To make engines more fuel efficient and environmentally friendly, engineers must increase the bypass ratio. This means they must make the front fan even larger, allowing more air to bypass the fiery core. But commercial aircraft are not getting taller. The landing gear can only be so long, and airport infrastructure is already maxed out. If the engines get any wider, they will literally scrape against the runway tarmac. We have completely run out of physical space beneath the wing. So, how do aerospace engineers break a limit they cannot build around? They do the unthinkable. They strip away the outer casing entirely. Welcome to the open fan architecture. Advanced prototypes currently in development by major aerospace consortiums look less like traditional jet engines and more like highly swept, futuristic propellers. By removing the heavy, restrictive outer shell, the carbon fiber fan blades can stretch wider than ever before, promising a massive, unprecedented leap in fuel efficiency. But this radical design resurrects a terrifying old problem. If you remove the massive outer casing, you also remove the ballistic Kevlar containment ring. How do you safely contain a catastrophic blade failure at supersonic speeds when there is no shield left to stop the shrapnel? That is the next great, high-stakes puzzle engineers are currently rushing to solve. Simultaneously, the firestorm inside the core is about to undergo a violent evolution. The global aviation industry is looking toward a zero-emission future, powered not by kerosene, but by cryogenic liquid hydrogen. Hydrogen is the most abundant element in the universe, but taming it for aviation is a thermodynamic nightmare. To remain a liquid, it must be stored inside the aircraft at -423 degrees Fahrenheit. Yet, it burns at extreme temperatures in the combustion chamber, leaving behind nothing but pure water vapor. The immense thermal shock of pumping one of the coldest liquids in the known universe directly into a roaring 600-degree inferno will require an entirely new generation of impossible materials. The thermal expansion and contraction alone would instantly shatter today's most advanced superalloys. Right now, as you watch this, thousands of commercial jets are streaking across the freezing stratosphere. Millions of people are sitting comfortably in window seats, reading books, sleeping, or drinking coffee at 35,000 feet. Just a few feet outside their window, a colossal, carbon fiber blade is slicing the freezing air, feeding a continuous, violent firestorm that should, by all laws of nature, melt the very metal containing it. We have normalized an absolute miracle. We have trapped a hurricane and a star beneath our wings. trusting microscopic crystals and invisible shields of air to bring us home safely. The sky has been conquered, but the frontier of human engineering has no end. Next time you board a flight, will you look out the window the same way? If you enjoy journeys into the hidden mechanics of our world, subscribe for our next documentary.